Okay, so now let's find some limits algebraically. So the first thing we always want to try to do is direct substitution. So let's look at the first one. The limit as x approaches 5 of 2 is equal to what? So this is using that first of the basic limit rules that I gave you. So the limit of a constant, no matter where you're at, the limit of a constant function is going to be that constant. So in this case, because 2 is our constant function, so think of this as a horizontal line, f of x equals 2, then we know no matter where we are on that line, so if we're coming into x approaching 5, we know this limit is going to equal to 2 because this is a constant function. For the next one, limit as x is approaching 4 of x cubed. This is that third rule, so we can just direct substitute. So this becomes 4 to the third power. Notice because I've direct substituted, I have found that limit, and so I'm dropping that limit notation. So you have to keep that limit notation until you're directly substituting in. So in this case, we're subbing in 4 to the third power, and so we evaluate that and we get 64. So the limit as x is approaching 4 of x cubed is 64. The next one, limits x approaches negative 1 of 3x squared minus 5x plus 2. So this is a polynomial, so we can direct sub. And so we're going to substitute in negative 1. So this becomes 3 times negative 1 squared minus 5 times negative 1 plus 2. And working through this, so negative 1 squared is 1. So that 1 times 3 becomes 3. Negative 5 minus 5 times negative 1 just becomes plus 5 plus 2. And so we end up with 10 for this limit. So the limit as x is approaching negative 1 of 3x squared plus minus 5x plus 2 is 10. The next one, D, so we've got a rational function now. Limit as x is approaching 5 of x squared minus 3x minus 4 over x minus 4. So again, we want to try to directly substitute into this and see what happens. So we sub in our 5. We get 5 squared minus 3 times 5 minus 4 all over 5 minus 4. Looks like direct substitution is not going to work. We're not going to end up dividing by 0, so we don't have an issue here, so it works. So this is going to give us our limit. So 5 squared is 25. 5 times 3 is 15. So 25 minus 15 minus 4 all over 5 minus 4 is 1. And so then this just simplifies to 25 minus 15 minus 4, which ends up being 6. Limit as x is approaching negative 8 of the cube root of x. So again, direct substitution. In this case, we're taking the limit as x is approaching a negative number. So we look at the index to make sure we're good. Index is 3. We're good because it's an odd index seed radical. Remember, if this was an even index, you couldn't plug a negative into, or you couldn't end up with a negative under your radical. So, but we're good in this case. So this direct substitution, we end up, this is the cube root of negative 8. And cube root of negative 8, we know is negative 2, because negative 2 to the third power is negative 8. For the next one, the limit as x is approaching 16 of the square root of x. So again, direct substitute, so square root of 16, and that's just 4. So think about what this means. As you come into x, going to x is approaching 16, f of x, or your y's, are approaching 4. For the next one, limit as x is approaching 3, the cube root of x squared minus 3x, the cube root of x squared minus 1. So substitute 3 in, so this becomes the cube root of 3 squared minus 1. So that's the cube root of 9 minus 1, which is the cube root of 8, which we know is 2. Now let's look at h. So the limit is x is approaching 0 of square root of x. Now, it's tempting to just say, okay, I can find the square root of 0 and try to direct substitute. So if we substitute in, this becomes square root of 0, gives you 0. Okay, so maybe the limit is x is approaching 0 of the square root of x. But remember, to be able for this limit to exist and to be going to 0, you would need to evaluate the two-sided limits, the two one-sided limits, and have those limits be equivalent to each other. So, okay, limit as x approaches 0 from the right of square root of x. That's not an issue. That is the square root of 0, which is 0. That's not an issue. But now let's think about what happens if you take the limit as x is approaching 0 from the right of the square root of x. So if you think about this, square root of x, we're coming into 0 from the left-hand side. So that means we're going to be coming in from negative numbers. And what's the square root of a negative number? It's complex. So because it's complex, you end up with non-real numbers. So this limit does not exist. And remember, if you think of this graphically, your graph of square root of x, what's it look like? So if this is our x and y axis, square root of x starts at 0, 0, and then goes off like that. There is nothing at all over here on the left-hand side. So because we cannot come in, we can come in no issues. We can come in all day long coming in x is negative. But we can't come in over here. There is nothing. So that limit cannot exist. So be careful. This is one of the times where direct substitution will lie to you. If you try to direct substitute into that limit, you can solve it. The issue is the two one-sided limits do not agree here because one side does not exist. How about the next one? The limit as x is approaching negative 2 of the square root of x squared minus 1. So we've got a negative number out here that we're trying to substitute into an even antecedent radical. But remember, the issue comes when it's the square root of blah. So the blah itself cannot be negative. That doesn't mean x can't be negative. So we can still substitute in negative 2 here. So if we substitute in negative 2, this becomes the square root of negative 2 quantity squared minus 1. Don't forget your parentheses around the negative 2 because otherwise you're just saying that 2 squared, so it'd be negative 1 times 2. So make sure you're using parentheses there. And so we do that. Well, negative 2 quantity squared is 4, so this becomes the square root of 4 minus 1, or the square root of 3, which is a real number. So this limit exists and is the square root of 3. It's not the endpoint of this radical, so we're good. Now for some trig ones. So the limit as x is approaching pi of 3x cosine x. So no issues plugging in. So if we think about this, this is a product here. So this is 3x times cosine x. So then we can rewrite this using our product rule. So the limit as x is approaching pi of 3x times the limit as x is approaching pi of cosine x. And remember, so if we think about whether or not direct substitution is going to work here, and then we need to think about, okay, what type of functions are these? So this 3x, f of x equals 3x, that we know is a polynomial. We can direct substitute, no issues. Cosine x, so g of x equals cosine of x. We know cosine of x, the domain is negative infinity to infinity, so we can direct substitute anywhere in the domain of that trig function. So we can direct substitute. So we can direct substitute into this, and we'll get out an answer just fine. Now, also notice that I carried the limit notation through right now because I haven't evaluated that limit yet. I have not substituted in for my pi yet. I haven't done anything to find the limit, so I have to keep on going with the limit notation. So now, though, I'm direct substituting, so I'm plugging in pi for x. So this becomes 3 pi for the limit as x is approaching pi of 3x times now cosine of pi. So now, because I've evaluated that limit, now I can drop that limit notation because I now have that limit. We just need to clean it up a little bit. So we have 3 pi, and we know cosine of pi is 1. Or sorry, cosine of pi is negative 1. And so because we know that, so we end up with this limit is equal to negative 3 pi. All right, for the last one, so the limit is x is approaching pi of 3x plus cosine x. And you can think of this as if there's parentheses around this entire thing. So we're taking the limit of this entire piece. So limit is x is approaching pi of 3x plus cosine x. Then, again, we could split this up into the limit as x is approaching pi of 3x plus the limit as x is approaching pi of cosine x. And so if we do that, now we know limit as x is approaching pi of 3x. We've already established we can direct substitute, so that just becomes 3 pi plus, and then the limit as x is approaching pi of cosine x. Again, we can direct substitute because at pi is in the domain of cosine of x. And so this becomes cosine of pi again. So this becomes 3 pi plus -1, which then just becomes -1 plus 3 pi. Or you could leave it as 3 pi plus -1. Either way is fine. And for the last one on this page, so the limit as x is approaching 0 of e to the negative x times sine of pi x. So same idea, split it up into the product. So this becomes the limit as x is approaching 0, e to the negative x times the limit as x is approaching 0 of sine pi x. And so when we go to evaluate this, so think about direct substitution again for exponential and trigonometric functions. As long as it's in the domain, then we can direct substitute. So in this case, 0 is in the domain of both e to the negative x and sine pi x. So we can direct substitute. So this becomes e to the negative 0 times sine of pi times 0. And so e to the negative 0, which is just e to the 0, anything to the 0 power is always 1. That's right. So this is 1 times sine of 0. And so we know sine of 0 is 0. So this is 1 times 0, which just then gives us 0. All right. Last one. So the limit as x is approaching 1 of the natural log of x over e to the x. This one you have a couple choices in how you want to do it. We can use our logarithm properties, rewrite this logarithm first, or we can just go ahead and direct substitute in, because remember, 1 is going to be, in this case, 1's in the domain of x, 1's in the domain of e to the x. So then when we can substitute into that, then that stuff's going to be positive, so it's in the domain of natural log, so we're good. We could direct substitute in. Or, so you can do it either way. I'm going to do it both ways just so that you see both ways. So if I try to rewrite this using my logarithm properties, so then this becomes the limit as x is approaching 1 of, so natural log of a quotient, remember, is the difference of the natural log, so this becomes the limit as x is approaching 1 of the natural log of x minus the natural log of e to the x. And so then this gives us the limit as x is approaching 1 of natural log of x. And remember, natural log and e are inverses of each other. So by the inverse properties from 171, then the natural log of e to the x just becomes x, because the natural log and e undo each other. Think of it the same way as square root and squaring, or cube root and cubing. Same idea. So then this just becomes minus x. And now we can direct substitute. Again, 1 is still in the domain of natural log x, so we're fine. So then this becomes natural log of 1 minus 1. Now be careful. It's easy to sit here and say, okay, I'm done. I found the limit. But don't forget, you still have to simplify. You should always simplify as much as possible. And if you don't simplify, you're going to lose points. So in this case, what what can we simplify? So in this case, we know natural log of 1 is 0. So this just becomes 0 minus 1 or negative 1. Now what if we did this the other way? So limit as x is approaching 1, natural log of x over e to the x. So what if we just went ahead and tried to direct substitute from the beginning? Would we get the same answer? Well, math and logic tell us we should. So let's see how we would. So if we direct substitute, then this becomes natural log of 1 over e to the first power, or natural log 1 over e. So how are we going to simplify this? So remember, 1 over e, that's the same thing as saying, so now natural log of e to the negative first power, right? So using our exponent properties, because that's technically e to the first in the denominator, so using the negative exponent rule, bring that up, flip the sign of the exponent. This becomes natural log e to the negative first power. And then from here, we know, again, using that inverse property, natural log and e undo each other, and we're left with negative 1. So you do, in this case, get the same answer both ways, as you should. Because the function, if you rewrite it differently, if you've done everything correctly, you should still get the same value in the end, because the function is going to be approaching the same value no matter how you solve it, as long as your mathematics is correct.